This conference will now be recorded.
Well, hello, everybody. It's 11:30 Eastern Time, so we will get started. My name is Mike Ryan. I'm the Director of Sales and Marketing here at TX RX. Welcome to our webinar series. This is our second webinar out of 9 over the next year. This webinar will be 45 minutes. You will all be muted, so please enter your questions in the chat box, and then we will address those questions at the end of the webinar. Now I'd like to introduce you to Jim Grotke. Jim is one of our senior applications engineers that designs our custom RF conditioning systems. So Jim, please take it away.
Well, hi everyone. First of all, I'd like to welcome you all to the webinar. I'll be discussing the process that our application engineering team uses to design custom combiner and multi-coupler systems. Again, my name is Jim Grotke, and I'm an applications engineer for TX RX Systems in Angola, New York. Just a little personal background. I've worked at TX RX for about 3 years now, and I have over 3 decades of experience as an engineer, both in the LMR industry with TX RX and in other areas of electrical engineering. I'm really proud to be part of the TX RX team. I'm very excited to show you a little bit about our processes and how we develop custom systems and solutions for the customers. If you have any questions, we'll try to answer them in a timely manner. But the Toolkit is a custom software package and database that we developed in-house to help us with our custom designs. So let's get started. Our agenda is we're going to talk a little bit about initial steps. We'll look at the Toolkit main entry screen. We'll discuss a new Toolkit entry process, go through the design phase, talk about what we do after we complete the design, and then contact information and questions will be at the end. So our Toolkit allows us to create accurate designs in VHF, UHF, and 7, 8, 900 megahertz bands. It helps us to get a design package together quickly and efficiently. But engineering expertise is still required because we will need to review results and make educated decisions based on the requirements, the frequencies, site considerations, and any other requirements that the customer may have. So a request for a quote will be sent to TXRX, and it'll either be through the website or through a salesperson. A completed requirement spec document, we used to call them questionnaires, is required so we can efficiently design a system that will meet customer requirements. It'll be reviewed for completeness, and if there are any questions, the sales team will contact the customer. A new Toolkit entry will be generated along with a unique Toolkit number, and we use that Toolkit number as a reference for the RFQs and for the designs. Any special notes will have to be entered into the Toolkit entry appropriately, and then the applications engineers will review that request, and if they have any other questions, mainly on the technical side, they'll contact the customer. Otherwise, they'll get started on the design. So here's a quick shot of the Toolkit main entry screen, and this is where the statuses can be quickly reviewed. We use SharePoint to keep track of the RFQs and customer project information. So basically, a new Toolkit number will be generated when the new Toolkit entry is made, and it's just a sequential number. And then with that, there'll be a documents folder in the Toolkit entry, and that houses all of the customer requirements, any correspondence, any technical information, any other information that we need to do the design. And then we also have over here a link to our phase 4 design, which is our computer-aided design software. And that link will take us to get to our to when we start doing our modeling and designing. So when an engineer starts the design, a custom engineering number needs to be generated, and that number will be a reference for that design. The first 2 numbers here, 20, indicate the year that the design was started, and the next 3 numbers are a sequential number for that year. Afterwards, we'll develop a model number. In this case here, a model number, it starts out with the system type. 74 indicates a combiner multicoupler system. Then the frequency band, 70 indicates 450 to 470 megahertz. And then the engineering number or custom number. Then rack information. In this case here, LR stands for less rack. The customer will be actually supplying that for us in this instance, and they will need to provide us with all the specifications that we need so we can configure the design so it will mount into the equipment that they have. And then this is some type of indication of the project or site information. So after we get this established, we'll open the phase 4 link to start the computer-aided design software. Now keep in mind the examples that I'm showing here are using bits and pieces of designs to help illustrate our system. So they may not seem to match, but it gives a better indication of the considerations that we need to account for. And it also shows the fact that we can design from the UHF all the way through from VHF all the way through the 900 megahertz range. So when the modeling software opens, this is a window where we'll start adding antenna information. And this is really a very important requirement that we need to have the customers provide in that requirement spec document. Single or separate TX RX antennas, vertical, horizontal spacing, and gain, they all have a big impact on the design. Now, we prefer to have separate TX and RX antennas because this helps reduce possible intermodulation interference, and it helps reduce the need for extra filtering. You know, sometimes more than one TX antenna is needed too. In a case like that, if there are IM issues, splitting the interfering frequencies between the transmit antennas can help reduce interference possibilities. Or if there are close transmit to transmit frequencies, they can be split between the antennas, which would help in reducing insertion loss and the possible need for hybrid couplers. You know, the better the TX and RX antenna separation, the more isolation you have. And horizontal spacing isn't as good as vertical spacing, tip to bottom, you get better isolation. Also, antenna gain affects what the total isolation you get from antenna separation as well. This is the page where we enter frequency and channel information and radio information. So the radio type, radio function, modulation, frequency information, power information is all entered here. We will assign the antennas appropriately to the TX and RX channels. So here we talk about radio information. That basically tells us what type of radio, being it VHF or UHF or whatever. The radio function is whether it's a repeater, a transmitter only, a receiver only, base station. And all that information is used by the software to calculate the proper isolation requirements that will be needed for the system. The modulation information is used to help when calculating the intermodulation potential interference in our IM studies. We also, over here, we have a couple other tabs, channel spacing and spectrum DNA tabs. And that's information that we use to help us with the more in the design details. So this is basically the channel spacing tab. And over here, you can see it provides us with transmit to transmit spacing, both between channels and overall spacing. This gives us information on the receivers with receive to receive channel spacing and overall receive frequency bandwidth. And over here, we have the overall transmit to receive spacing or transmit to receive guard band. And this gives us an indication of what type of potential issues we may have if we have close guard bands and other considerations that we may need to take into account when we go through the design. And this is a shot of the spectrum DNA, and it's really basically a graphical view of the frequency plan. You can quickly view at and see what the TX and TX to RX spacing is in a graphical format. So after we set up the channel and antenna information, we'll go to the Intermodulation Report tab. And this lets us know if there are any IN concerns. Intermodulation is a result of mixing of two or more signals in a nonlinear junction or device. And these products can be extremely destructive to communications. The main concern really is third order IM because that usually produces the highest signal level. And here are a couple of examples. So over here we have what we consider a relatively clean IM study. There's no third order hits and nothing that we really need to be concerned about. But over here, the way the frequencies are added together, you have potential IM interference issues. You can see there are some third order hits. When we run into a situation like this, we'll get back to the customer and let them know of these issues that may need to be addressed. And we'll send a copy of the actual report as well to get more information as to how to proceed with them. But we're going to get more in-depth discussions with intermodulation issues in a future webinar. This is a copy of the IM report that does get sent to the customer, and it will show the frequency layout, the transmit and receive frequencies. And I chose the one that had third order hits to give you a quick view of how it's determined. So you add the first two frequencies together, and then you subtract the third frequency, and you come with an intermod product. In this case here, it's 466.95, which is only 25 kilohertz away from the receiver of 466.925. So there's a good chance we're going to have interference with that product on that receiver. And again, we'll discuss this with the customer, and we may be able to suggest some possible remedies. We could potentially move, if there's more than one antenna, we could move the offending frequencies, split them up between the antennas, or maybe the customer has a different frequency plan that they can provide for us to continue the design with. So now we go into the ISOMA tab, and ISOMA stands for isolation matrix. And this is where we select the filtering required to suppress the transmitter noise and prevent the receiver descents. Transmitter noise is broadband sideband noise generated by a transmitter when it's keyed up. And this noise can cause carrier overload and reduce receive sensitivity. Carrier overload is excessive carrier power in the receiver front end, and it's also known as receive descents. So it's really important in a combining system to minimize the impact of that transmitter's noise on a receiver, and of course the impact of the receiver's sensitivity to a particular transmitter. So our filtering schemes are designed to suppress the transmit noise at the combiner and to provide filtering on the receive side to prevent any of that noise, transmitter noise, to get to the receiver. Now I usually start on the transmitter side when I start my design, and so over here, this is the transmit noise side. And over here, we have a drop-down box where we can select the filtering that would be required. In this column here, we show the transmitters that we're trying to isolate from the receivers and their associated antenna. Here are the receivers we're trying to protect from that transmitter and its associated antennas. Here is the information of isolation that's provided by antenna separation. And then this here shows the overall noise protection that is required to prevent any interference between transmit and receive. And this is all determined through the software by the information from the frequency plan, antenna separation, and TX to RX guard band. The closer the TX to RX frequencies they are, the more isolation is required to prevent any noise. And then you have this column here, which shows the overall separation between the receivers and the transmitters, and then the additional noise filtering that's going to be required. So the modeling software is really complex, and it's designed to account for frequency band, antenna separation, TX to RX guard band, and available filtering. The actual filter curves are shot in the data, and the data is put into the software. And then this software will provide available filters in the frequency range that we're working with that we can select to obtain the required isolation that we need. So This is starting the transmitter selection process. We'll go into the drop-down box, and it will give us a selection of filters that we can use. And the software will then look up the curve data and provide isolation information at that specific frequency and the transmit to receive separation. Now we have thousands of different filters and each have dozens of curves for different settings. And they're in a massive database. And when we select the curve and any spot on the curve, we'll be able to see the isolation it'll provide. However, it's still up to the engineer to review other information such as the transmit to transmit frequency separation and select the proper filter information to ensure that there's no interference between transmit channels. There are a variety of filters that can be used depending on the overall frequency plan, but we always start with a T-pass filter on the combiner. And then after we select that filter, and we'll use one of the selection buttons here, it will calculate the actual isolation that is provided by that filter at those frequencies and that separation. Then we'll determine if we're going to need extra filtering. And we'll look to see we have other choices that we can use for this, such as bandpass filters or vari-notch filters or series notch filters. And we'll take a look and see, for instance, a bandpass filter might really be a good choice if you have receive frequencies that are all pretty much the same separation from the transmitter. But a vari-notch filter might be a better choice if you have a particularly close receiver to a transmitter. So once we hit the selection again, it'll make the calculations and then it'll add all of the filter isolation calculations into the box over here. And if it becomes green, that shows that it either meets or exceeds the minimum requirements. And this is really a powerful software tool, and we can quickly access the thousands of curves that'll fit for the best fit for the conditions. And we can easily change our design schemes. We'll move filtering around, change from bandpass to vari-notch, and it'll help with us to help determine a more efficient or a better overall design. So this is kind of a quick view of what the curves actually look like. This is a shot of a bandpass curve. You can see different insertion losses here, and the higher the insertion loss, the tighter the bandpass. And then this is a quick look at a vari-notch curve, and again, as you can see, the further your frequency is away, the deeper the notch that you can get. And the ISOMA software uses all of this information when it calculates the isolation that's actually provided for the frequencies chosen. Then we'll move along to the receive side, and we'll basically follow the same process. Drop down box and look at the filter. But this is where, again, the engineer needs to decide what is the best method to do this, be it a window pre-selector or maybe channelized like the TX side, and a lot of factors are accounted for, such as the overall bandwidth, the TX RX guard band, and maybe even physical space considerations. In this example, the overall spacing is about 1.75 megahertz, and a 2 megahertz wide milled filter is going to work very nicely. And the software will look up the curve for this filter, and when we select it, it'll provide the information and calculate the isolation based on the parameters provided. And essentially, when all is said and done, we want to make sure everything over here looks green, and we want to save and save often. But the engineer still needs to review what the results are here and make sure that they're going to meet or exceed the minimum requirements. But once we get done with this, then it's time to establish through-line cable information and establish a drawing. And this is kind of what the drawing looks like. It's an electrical representation of, get it here, an electrical representation of the design that we just did. You'll see the milled filter here, the amplifier, and then the multicoupler to branch off to the different receivers. And then here is our transmit combiner, where we use our T-pass filters, our vari-notch and bandpass filters and isolators and such. Now, I didn't show insertion losses or the critical cable lengths and the through lines. That's all going to be discussed in the future webinar and how that is all determined. But we also, though, provide a specifications chart on the drawing as well that shows the required isolations and the actual designed isolations that were achieved with what we did with the software. So basically, once we have all that together, we consider the design complete, and it'll be configured from that drawing. It'll be configured and entered into our ERP system. And then a configuration number will be generated. And after this configuration is established, we'll review it and make sure we've met all the requirements needed. And that configuration number will then be entered into the toolkit and consider the design complete. Once that happens, the sales department will then retrieve all the pertinent documentation, the configuration number, and use that information to determine cost and prepare and issue the quote. Now, in the future, we can go back to this toolkit and we can refer to that design and any other special notes if necessary, or if a modification of that design is required. We have access to all of that original information in that database that we keep, and we can more efficiently make changes or modifications or expansions to that design. And again, this will allow us to create accurate designs in VHF, UHF, and 7, 8, 900 megahertz bands, and it helps us get together a package quickly and efficiently. But engineering, I got to keep stressing, engineering still needs to review the results, and we have to make educated decisions based on the requirements, frequency, and all the specifications and considerations that were provided by the customer. And basically, that's about it. We really like using this because it really helps us out. It helps us keep track of anything that we've done and all past designs because of the huge database that we keep. And we can, again, quickly access information and make any changes as necessary. If you have any questions, please enter them. But otherwise, thank you very much for attending.
Jim, thank you. This is Mike Ryan again. So if anybody has any questions, please enter them into the chat box. You'll see the chat icon in the the circle with a point coming out of it in the upper right part of your screen. So we'll give people a couple of minutes and wait for any questions.
Okay, I see a question from Jesper here. Well, yes, okay, so depending on the complexity of the design, it could take up to a couple of days. By the time we review the information, we compile all the results, we have the configuration. Sometimes it can take a couple days. Typically, 1 to 3 days is the maximum amount of time that we'll run into it. And our design package, well, that will include the drawing, it will include the quotation, it will include through-line cable sheets, it'll include the intermodulation study.
And Jim, Mike Ryan here, maybe you could talk a little bit about the questionnaire, the spec sheet, and the importance of the accurate information on there to
Yes,
keep the design time down to a minimum.
Yes, we do really ask that the customer sends out fills out a questionnaire, and it usually gets sent to them with a request if they don't already have it. And we ask them to fill out all the information. It gives us site information. We ask for any information if it's an existing design. We ask for the frequency information and the frequency plan, antenna information, antenna separation information, and mounting information. All of that is extremely important, because if we have to keep going back to try to get more information, then it slows down our design process.
And Jim, here's another question.
Yes.
Are you guys no longer using a gold anodized color on your filter?
Right, we are no longer using that because that goes with RoHS compliance, to stay with RoHS compliance.
And another question about whether or not this presentation, this webinar will be available. The answer to that is yes. We are recording it and we will send a link out to all of the participants afterward. Jim, here's another question. Do you consider space requirements at the sites?
We will consider space requirements if the customer provides them. If they have specific considerations, we'll do our best to meet that. But space quite often depends on the frequency plan provided to us. Separation of transmit to receive frequencies, number of channels, number of antennas provided, and antenna separation. So we can fit things into a small space if we have really good frequency plan and a lot of and don't require a lot of filtering. But if we have a bad plan, maybe we want to tell the customer that it's going to actually be in a big footprint.
Any other questions? Okay. Give it a few more seconds here for people to type in any other questions they may have. Well, all right. It's 10:56. We will 11:56 Eastern. We will end the webinar at this point. Again, thank you for everybody for your attendance and your questions. We will be getting an email out to you with the link to this recorded webinar. Have a good day.